Yeah.
Hi, everybody. Thanks for coming. Today we have Leap's very own Hong Fan. Hong is a postdoctoral researcher at Columbia. He received both his PhD and bachelor's degree in atmospheric science from Nanjing University of Information Science and Technology. And his research focuses on leveraging machine learning and latent space methods to improve data assimilation and weather forecasting. So excited to
Thanks
hear you
for
take.
the introduction, and thanks everyone for coming. Today I'm going to share my PhD work about using the machine learning to improve the data simulation. So at first, I want to introduce what is data simulation. So a really classic definition of data simulation is that it uses all the available information to get and fuse them to get the most accurate state estimation of the dynamic system, including the atmosphere and the ocean. And for the atmosphere, there are two main purposes for the data simulation. So first is to provide an accurate initial state for the numerical models. And the second is to provide a physical consistent and high quality real nasty data set for the climate research, such as the ERA5. And if we look into this definition, we'll find that the key of the data simulation is about use all of the information and how to fuse them. So the first question is that what information do we have? And if we focus on this, we'll see the roadmap of the development of data simulation. So at the very beginning, we only have the sparse observations. So at that point, we can only do the interpolation to get the estimation of the whole fields, but this is very empirical and it has a large error. And then people just realized that we can use the climate mean as a prior, and we can correct it based on this as a baseline. And we also call this the first guess of the fields. And so we correct the grid one by one with surrounding observations, and we call this method the successive correction method. And almost at the same stage, the numerical weather prediction systems emerged. And now we can use at that point, we can use the forecast result as the prior instead of the climate mean. And we usually call this the background fields in the data simulation. But this method is very empirical because we only we calculate the weights for the observations and depends on the distance. So how to do the correction more mathematically rigorous? So we have to introduce new information. That is the error estimation of the background fields and the observation. And since high dimensionality of the atmosphere, we usually assume that the error of the background fields and the observation are Gaussian distributed. So based on the Bayesian theory, you can have this equation to solve this data simulation problem, and we call this the optimal interpolation method. And this method has been applied in the ECMWF for about two or three decades. And it's really good, but with the development of the forecast model, we have a high resolution forecast model. And also we have a lot of indirect observations, such as satellites. So this method is not enough to deal with these situations. So I have to switch to solve this problem by optimizing this cost function. And that is a three-dimensional variational data assimilation method. So it's mathematically, it should have the same results as the optimal interpolation. But the three-dimensional variational method, they have different realization. Sorry, they have different they have some difference in their realization. And the 3D they get solve the whole fields simultaneously, while the optimal interpolation is also is to correct the field one by one with surrounding observations. So the 3D will have more consistent analysis field. And in both optimal analysis and the very early 3D VAR, we use the static estimation of the background error covariance matrix, which is a B matrix here. But the real forecast error should evolve over time, and that's called the flow dependency. So how could we consider this real-time flow dependency? So we have to introduce the ensemble forecasting to provide the real-time information. And based on this, we had the ensemble Kalman filter. And I have to mention that all of these methods are three-dimensional data assimilation method. That means that we only perform data assimilation when we have the one step. We only assimilate one step observations per data assimilation step. And if we want to assimilate all the observations or series of the observations at the same time, we have to introduce the model dynamics. And that is the most famous data assimilation method, which is called the four-dimensional variational data assimilation method, which is 4D-var. So 4D-var not only enforce that the first initial analysis close to the observations at the data assimilation step, but also enforce that its upcoming forecast close to the future observations. So the whole trajectory could get close to the truth. And this is the foundation for the ERA5, and this method has been the operational, the state-of-the-art operational data assimilation method for decades. So why data assimilation don't have methodology breakthrough in recent decades? The main reason is that we didn't introduce new information, right? But now we have extensive accumulated historical data, and now we have really advanced machine learning method. So it's time for us to have some new breakthrough in data assimilation with this machine learning and historical data. And then I want to introduce the main challenges in the atmospheric data assimilation. The first is about the physical consistency of the analysis. So when we want to correct one grid, or one variable, we have to also correct the surrounding grids to ensure all other variables. So to ensure that the final analysis is physically consistent, right? And in the traditional data assimilation method, we relies on the background error covariance matrix, which is called the B matrix, to realize this, especially its covariance part, which depicts the correlation between different variables. But this background error covariance matrix is super hard to estimate. The first reason is that the dimensionality of this matrix is super high. It's even hard to store. And what's worse is that in some data assimilation method, we have to calculate its inverse. And the second reason is that, as I mentioned before, that the background error should evolve over time, right? So it should vary with different weathers. So it's hard to estimate. And another challenge comes from the increasing resolution of the numerical weather prediction models. So with higher resolution, we have to consider more nonlinear features and non-Gaussian process, and that is hard for data assimilation, because most of the data assimilation methods assume that the error are Gaussian distributed. And also with this trend, the computational cost will rise very rapidly. Because of the model resolution is much higher. So in this work, we want to use the historical data. We want to use the machine learning to solve these two problems, and we propose the latent data assimilation. So latent data assimilation relies on a neural network called the autoencoder. It comprises of two components. The first is encoder, which can compress the high-dimensional input model state into a low-dimensional latent space, and the decoder can recover it back to the model space. And to train this model, we have to minimize the distance between the reconstruction and the input, so that the latent variables could compress as much information as possible in the model space. And the latent data assimilation is to fuse the observation information in this latent space. And it has two potential benefits. The first is that because the process of the compression, the internal relationship between the model variables could be learned during the process of the compression learning, right? And so we will not rely too much on the background error covariance matrix to realize the physical consistency. And the second potential benefit is that the data assimilation could be more efficient if we perform it in this much smaller space. But the main problem for the data assimilation is that how could we assimilate observations in this latent space, which is unexplainable. And here we have three methods to realize this. The first is called the variational method, and the second is called the observation to latent space method, and the third is the generative data assimilation method. So we first introduced the variational data assimilation method. And before that, I want to show the pipeline of the latent data assimilation. So when we have the background field, which is weather forecasting, it usually have a large arrow. And we use the encoder to compress it onto the latent space to get the latent background. And then we fuse it with the observations to get the more accurate latent analysis. And then we use a decoder to get the final analysis in the model space. And the variational latent data assimilation, for the variational latent data assimilation, we define two cost functions. That is the 30var and 40var in the latent space. We call it the latent 30var and the latent 40var. And to solve these two cost functions, it can be optimized automatically in the deep learning framework because we have the autograde and backpropagation algorithms without any adjoints or the tangent linear matrix. But the drawback is that since we have to solve this problem in the deep learning framework, so all of the operators in these two equations should be differentiable, including the observation operator and the forecast model in the latent 40var. And when we compare this cost function with the original 30var and 40var in the model space, we'll find there are two main differences. The first is that since now we perform data assimilation in the latent space, so we have to calculate the background error covariance matrix in the latent space instead of in the model space. And secondly, that in this observation term, we have to introduce a new operator that is a decoder of the autoencoder. That we have to project the latent state back to the model state at first, and then use the observation operator to map it to the observation space, and then we can compare it with the real observations and calculate the distance between the observation and the latent state. So we have to introduce a new neural network here. And here I will show that how we realize the latent 40var for the global atmosphere. So the first is about the observation operator. And in this proof of concept work, we only assimilate the surface observations and the radio sound observations, which is super easy. So we can just use the interpolation to build this observation operator. But I have to mention that this operator could be really complex when we use the indirect observations, such as the satellite. And for the decoder, which is a part of the autoencoder, we learn this. We train this autoencoder on the YARI5 using 5 upper AL variables and 4 surface variables. And the backbone of the decoder of autoencoder, for the backbone we use the swing transformer. And the latent size we set the compression ratio of 32. And for the forecast model here, since it should be differentiable, and here we choose to use the machine learning-based forecast model. And we train the model, and the backbone we refer to the full model, which is an advanced mid-range weather forecast model developed in Shanghai lab. And the last step is to estimate the background error covariance matrix in the latent space. Although the latent size is much smaller than the original model space, we have a compression ratio of 32, but the latent space is still very large, and the background error covariance matrix in the latent space is large, and it's still very hard to store and calculate its inverse. So the first step is to simplify the background error covariance matrix in the latent space. And really surprisingly, we find that the background error covariance matrix in the latent space is almost decorrelated, and the matrix is almost diagonal. Here we show the variable correlation and the spatial correlation in the latent space. And in comparison, this is the variable correlation and spatial correlation in the model space. So you can see that it's really complex. And in traditional data assimilation, it's hard to simplify, and we have to use some tricks and have use some assumptions to simplify this matrix. But in the latent data assimilation, we can just assume that this is diagonal. So it's really easy for implementation. And we might have concern that, as I mentioned before, in traditional data assimilation method, we use the covariance part of the background error covariance matrix to enforce the physical consistency, right? But in the latent data assimilation, we ignore the covariance part. So will the latent data assimilation be physically consistent? And to answer this question, we perform the single observation experiments based on the latent 30var. And in these experiments, we only assimilate one observation. That we assimilate observations on 500 HPA for the geopotential height. And here we show the increment of the geopotential height and wind induced by this observation. And here we perform the data assimilation experiment on 2 cases, one in the northern hemisphere and one on the southern hemisphere. And we can see that the temperature increment and the wind are really consistent. And what's interesting is that in the northern hemisphere, the wind direction is clockwise, and in the southern hemisphere is counterclockwise. And this is because the model has learned the geotropic balance. And since the Coriolis force is the opposite in northern and southern hemisphere, so the increment wind should have this opposite direction. And here we also show the temperature increment induced by assimilating this observation. And also we show the background winds. So we can see that the temperature increment is really consistent with the background wind, right? And it's the distribution are quite different for different cases. And that is so-called the flow dependency. So in this experiment, we show that even with a static and a diagonalized background error covariance matrix, the latent data assimilation has inherent geotropic balance and flow dependency, which is hard to achieve in traditional data assimilation method. And then we evaluate the performance of the latent 40var both for the real analysis and the forecasts. And here we assimilated the real observations and validated the results with the real observations. And the conclusion is that for most variables, and here the red line is our method, and the blue line is the 40var in the model space. And in these 2 plots, lower is better. So we can see that for most variables, the latent 40var outperforms 40var, and in both analysis and the forecasting. And then I want to introduce the second latent data assimilation method, which is called the observation to latent space method. We call it OTL for short. And it's different from the variational latent data assimilation method, which only relies on the autoencoder. Here, we introduce a new neural network called the OTLNet to directly realize the mapping between the observation space and the latent space. And to train this model, we have to pre-train the autoencoder at first. So with a trained encoder for each sample, we can get its latent representation, right? And at the same time, we can use the observation operator to get the pseudo observations from this sample. So for each sample, we can have the pseudo observations from the observation operator, and we can have the latent representation from the learned encoder. So with this data, we can directly learn the mapping between the observation space and the latent space. And with these 2, also I want to mention that this framework is a self-supervised learning framework, because for both the autoencoder and the OTLNet, the input and the output comes from the same sample. And also we don't use the real observations in this process. So with these 2 neural networks, we can project both the background fields and the real observations onto the latent space, and then assume that their error are Gaussian distributed, and then we can use the Bayesian data assimilation method to get the latent analysis, and decode it. We'll have the final analysis in the model space. And when we don't have the background fields, or when we have the enough observations, we can also use these. We can use the observations to get the latent variables, and then directly decode it to get the final analysis. So this pipeline only use the observations and don't need the background fields. And we call this method the observation only analysis method. And this we call it the observation and background assimilation method. For this method, we call it OOA for short, and this is OBA for short. And to prove this concept, we apply this method on the mesoscale surface temperature, and here is our selected region. So it has very complex underlying surface with a lot of mountains and lakes, and the dimension for this field is 288 by 288. So it's a high dimensional field, and with high resolution, and we compress the surface temperature in this field into a latent space with a size of 24. So the compression ratio is super high in this case. And here we use a convolutional neural network to train the autoencoder. And since the latent size and the real observations are really small, so we just use the fully connected network to train the OTLNet. And here we show two cases that the reconstruction result with such a small latent vector. So the first sample is dominated by the surface temperature is dominated by the mountains, and the second in the second sample the surface temperature is dominated by the lakes and rivers. So we can see that no matter it's dominated by mountains or water or lakes, the latent space can compress it very well, and the reconstruction result is has a lot of details, and the quality is really high. So we think the 24 latent size is enough in this case. And we first evaluate the results of OA, that is only use the observations to get the final analysis. And here is an idealized case. The first plot is the label, and the other plots are the analysis inferred from the observations with different densities. And we can see that even with 9 observations, we can reconstruct the whole fields, the whole surface temperature fields with really high quality, with a lot of details, right? And then we evaluate this method with the real observations. In this region, we have 47 surface observation stations, and we only simulate 40 observations of them, and then use the rest 7 observations for validation. And we compared our result with the NCAR RTF-DDA data assimilation method, which is a traditional data assimilation method based on nudging. And we can see that our method is competitive with the traditional data assimilation method, even though we don't have the background fields. And also, we find that our method has fewer samples with large error compared to the FDDA method. And then we compared our method with the and then we evaluate the OBA method, which project both the background fields and the observations onto the latent space, and compare this method with the observation-only analysis method and the latent reservoir method. And in this experiment, the error estimation for the background fields and for the observation were estimated from the historical data. We first shows the case that we submitted 40 observations. And we can see that the OBA method and the OA method, the results are quite similar, and it's hard to tell which one is better. And when we compare the OBA with the VAR method, where latent reservoir method, we find that the OBA method is a little bit better. But the situation changes when we only simulate 4 observations. In this case, since we only have 4 observations, and that is enough to recover the whole field, so the OA method has large error, but the OBA method, since we also introduced the background information, so it has much lower error. And also in this case, the OBA has a significant improvement compared to the latent reservoir method. And here the yellow words, the letter shows the simulation time for simulating all of these 900 test samples. And the OA only costs 4 seconds, the OBA costs 9 seconds, and the variational method costs 30 minutes. And the main reason for this efficiency is that the latent reservoir it has to solve this problem by optimize the loss function. So it needs a lot of iterations. It's not efficient. But for the OBA method, since we project both the background and the observation onto the latent space, they are in the same latent space, so we don't need the variational method to calculate their distance. So it's much more efficient. So here's the conclusion that this method has high accuracy and it's super efficient. And then we scale this method up to the global atmosphere. And we have 2 main modifications. The first is that we start to use a time-lagged ensembles from the machine learning-based weather forecasting model to estimate the background error covariance matrix and the observation error covariance matrix in the latent space in a hybrid manner. And the hybrid here means the combination of the static error estimation and the real-time ensemble estimated error covariance information. And this is popular in the traditional data assimilation. And the second modification is that since now we have to consider more complex observations compared to the previous case, so we need a more complex OTL net, and we use a swing transformer to build the OTL net. The other setting of this method of this experiment is the same as the latent 40 var for the global atmosphere we mentioned before. And also, we find that the background error covariance matrix in the latent space and the observation error covariance matrix in the latent space is also almost diagonal. So it has two advantages. The first is that we can, if we assume that these two matrices are diagonal, we can perform data assimilation separately for each latent variable. So it could be super efficient for this method. And secondly, that since we have to only consider the variance, the diagonal part of the error covariance matrix, which is the variance. So we can use at least two ensemble members to realize the uncertainty quantification. And we evaluate this method using the cyclic data assimilation experiments with real observations. And the left plot is for the analysis, and the right plot is for the forecasts. So if you look at the analysis performance, our result is the red line here, and we compared it with the hybrid latent 40 var and the hybrid 40 var, which is the blue line and the black line. So we can see that our method can have better analysis performance compared to this four-dimensional data assimilation method. And what's interesting is that the yellow line here shows the error for the ERA5. And we can see that for some of the variables, our method can even surpass the accuracy of ER5. But it's hard for us to say that our analysis is better than ER5. We can only say that our method is more close to the observation system we have. And for the forecasting, the upper dashed line is a three-dimensional data assimilation method in both model space and the latent space. And here is the up and lower is the four-dimensional data assimilation method. And the red line is our method, our new method. They are all our methods. So the red line, we can see that it's competitive with the four-dimensional data assimilation method, and it's much better than the three-dimensional data assimilation method. And okay.
The H4D part, is that just using
the hybrid? H40 var.
Yeah, but the L is the lead.
H means the hybrid. Okay. So here we use the ensemble members to estimate the uncertainty, right? So we also use these for the 40 var and the latent 40 var for so it's fair. Yeah. And here we show the overall comparison of this method in the real observation case, experiments for the throughout the whole year in 2018. And the x-axis shows the assimilation time per observation step for simulating each observation step. So it's more close to the right. The method is better, and we can see that our new method is the most efficient method. So it only costs 1.3 seconds for each assimilation step, while the variational method costs 23 seconds at least. And the y-axis shows the forecast improvements over the 30 var, which is the baseline, which is the most traditional data assimilation method. And we can see that our new method is competitive with the four-dimensional data assimilation method, and is much better than the three-dimensional data assimilation method. And the size of this circle shows the GPU memory we need for this method. And we can see that this method is also the best. So it needs the lowest GPU memory. And the reason is that for the variational method, we have to save the parameters, the gradients during the process of the optimization. So it needs a large GPU memory. But for this method, it's kind of end-to-end method. So it's super efficient. And the last thing I want to emphasize is that this new method is a three-dimensional data assimilation method. That means that during the data assimilation process, we don't need to couple it with the forecast model. So it can be applied to any forecast systems, including the CPU-based forecast systems. Well, for the 40-var method here, we have to use the backpropagation, right? We have to use the deep learning framework for the optimization. So it can only be applied on the hybrid models, such as the NeuralGCM or the totally machine learning based models, such as the Pangu and Fuxi. And we want to emphasize, another thing we want to emphasize that is this method is inherently a combination of the end-to-end learning and Bayesian data assimilation. So in this method, we use the OTLNet, observation to learning space network, to directly learn the information from the observations in an end-to-end manner. And then we estimate its uncertainty. And then we combined with the background fields in a Bayesian manner. And I think that is the main reason why this method is the three-dimensional data assimilation algorithm, but it's competitive with the four-dimensional data assimilation method. And here I want to show the limitation for the variational and the OTL-based latent data assimilation method, that we assume that the arrow in the latent space are Gaussian distributed. Even though the OTLNet and the encoder of the autoencoder could be nonlinear and can solve some non-Gaussian distribution, but this assumption is still very strong. And here we show that if the prior is not Gaussian, and it had two modes, but we use a Gaussian distribution to fit this, and we'll find that the estimated posterior, this green line, is biased compared to the true posterior. And to solve this problem, we realized a third latent data assimilation method, which is based on the generative AI, that we use a diffusion model to learn this prior, directly learn this prior. And even though it's not perfect, but the estimated posterior could be less biased. So we train the diffusion model with in the latent space to learn the prior, and then during the process of the denoising or the generation, we incorporate the observation information as likelihood. And here is the results. So this is our generative latent data assimilation method. And we can see that it's much better than the three-dimensional data assimilation method, and it's a little bit better than the latent three-dimensional data assimilation method. And that means that we could have better results without the Gaussian prior. But I have to mention that this method is still a three-dimensional data assimilation method. Even though it can surpass other three-dimensional data assimilation method, it's not competitive with the four-dimensional data assimilation method because it's hard. And at this point, it's hard to consider the model dynamic in the diffusion model. It could, but it could be super expensive. And one step more, we want to use the reinforcement learning to improve this prior estimation. So here, this is the process of our previous work that we learned this prior distribution, and during the process of generation, we incorporate the data assimilation. So the posterior estimation, could be more concentrated, right, with the observation information. But in practice, we find that the learned prior could be a little bit wide. Not every region is good for the data assimilation. So inspired by the reinforcement learning in the large language model, we want to use the preference of the data assimilation that to tune this learned prior. So we set several metrics here, which is important for data assimilation. That is the analysis performance, forecast performance, and the physical balance. And then we generate a lot of samples from this prior. And then we can use these metrics. We can find which region is a good region and which region is the bad region. And then we use these samples to tune this learned prior. And we want it to generate samples more close to these win regions and generate less sample in these bad regions. So the tuned diffusion could have much better prior. So it's more concentrated. And with data assimilation, so we'll have more concentrated posterior distribution. And we show that for both analysis and the forecast, this method works. So it can improve both the analysis and the forecast. So this is and we show this all of these three latent data assimilation methods, and then we want to answer several important questions, really fundamental questions for the latent data assimilation. The first is that how the latent data assimilation achieve physical consistency. And to answer this question, we test the impact of the latent variables on the physical variables. And here we show that each latent variable can encode the combination of different physical variables. So, and for different latent variables, they encode different information here. And the first row is the mean, and the second row is the standard deviation. So it's really stable. And then we calculate the inner product of these rows, so calculate the inner product of the information encoded in different latent variable. And then we find that the matrix is almost diagonal. So this means that the latent variables can capture nearly orthogonal information. So they encode information in an almost orthogonal way. And I think that is reasonable because this is the most efficient way to compress information, right, in an orthogonal way. And this also explains why the error covariance matrix in the latent space is almost diagonal. And also, we conduct a really interesting experiment that we average one variable in the global atmosphere and keep other variables unchanged. Here we choose a Z500, and then we put this field into the autoencoder, and we can see that this average field can completely recovered and is almost perfect. Yeah, and this shows that the encoded latent representation has intrinsic physical consistency. Even though your input is not physically consistent, its output could be, if you project it onto the latent space, and its output could be physically consistent. So we find that the latent space, it has intrinsic physical consistency. So the latent data assimilation, no matter what method you use, it has intrinsic physical consistency. And also test this for the surface temperature case. And in this case, since the latent size is really small, it's only 24, so we can find that what's the meaning of each latent variable. And here we find that each latent variable represents a mode, right? Mode, and it's also really stable. And during the process of data assimilation, with the combination of several mean modes, we can get the analysis that get close to the final analysis we want to get. Yeah. And the second question is that why we can perform data assimilation in the latent space. Because the latent space is unexplainable and the decoder is nonlinear, so how can we guarantee that the optimal analysis in the latent space can correspond to a good analysis in the model space? And to answer this question, we test the property of the decoder of the autoencoder. And we find that the decoder of the autoencoder is locally affine. That means that the latent increment and its decoding model space increments are almost linear. And this is reasonable because for any continuous function, based on the Taylor expansion, it should be affine within a really small range, right? And we find that for data assimilation, the increment we need is within this range. So during the process of the latent data assimilation, it's almost the decoder is almost locally affine. Yeah. And based on this, we can mathematically prove that the latent 40var and the 40var have similar optimal analysis. This is also holds for the ENKF and latent 30 for the ENKF and the latent 30var. And this because this linearity, so it won't change the convexity of the loss function. So these two methods could have similar results. But we may have questions. So mathematically, they should have the same results. And for the latent 40var, we have some information loss, so it should have worse result, right? But why in practice the latent 40var is better than 40var? And we think the potential answer is that the latent data assimilation has better solution space than the traditional data assimilation. So in the traditional data assimilation, we mostly work on the model space, which has a super high dimension. But the real atmosphere only lies on the low dimensional manifold on this space. Not all the points on this space is reasonable. And if we assimilate in the model space, look at this. So when we have the background here or the observation here, if we just use the linear combination, we'll have the analysis here. and it's outside this manifold, right? So it's physically unrealistic. So for traditional data assimilation, we have to define the background error covariance matrix. We have to incorporate the model dynamic to rebuild the solution space and make it get close to this manifold. But this is hard because we have a lot of assumption here. We have a lot of empirical tricks here, so it's hard to realize this. And that is why some traditional data assimilation is not physically consistent. But for latent data assimilation from the perspective of machine learning, that the latent space directly learns this manifold. And since we have already learned this manifold and we perform data assimilation on this manifold, that is inherently physically consistent and more efficient and more easy to realize. And that is what I think why latent data assimilation is better than traditional data assimilation in practice. And at last, I want to share the main limitation of the latent data assimilation. There's no free lunch. Here we use the idealized surface temperature assimilation experiments for a mesoscale convection case to show its limitation. So the first plot is the choose of the surface temperature, and this plot is the background field. So you can see that it has a large arrow, and with the latent data assimilation, we can correct it. It's more close to the choose now. But this is a convection case, and within this black box, we can see that there's a convection here. And on the surface temperature, it has a cold pour. And for the background fields, since even though you don't have this convection, it's not correct, but it also has this cold pour structure. But even the choose and the background has this cold pour. In our analysis, this cold pour disappears. And the main reason is that we find that even the reconstruction of the choose cannot represent this cold pour. That means that the latent representation cannot compress these extremes, and this is I think this is reasonable because from the machine learning perspective and the manifold is hard to capture the outliers and the extremes. So this shows that the latent data assimilation is unable to analyze structures that cannot be represented with its latent space. And so for the extremes assimilation or the nonlinear assimilation, maybe we have to combine the latent data assimilation with other data assimilation methods to solve this problem. Yeah. And here is a recap and the reference. So here we first introduce a variational latent data assimilation method, which is a naturally decorrelated latent space. So we can simplify the background error covariance matrix estimation, and it can support the physically consistent data assimilation with higher accuracy. And then we introduce the OTL-based latent data assimilation that we directly learn an observation to latent space mapping in an end-to-end manner, and this can support the efficient and accurate three-dimensional data assimilation method, and is competitive with four-dimensional data assimilation method. And then last, we introduced a score-based latent data assimilation method. We use the generative AI to learn the prior and use the reinforcement learning to improve this prior. And our result is that it can get better posterior estimation, without the Gaussian assumptions. And that's all. Thanks for listening.
Oh, hi, Yang. This is impressive. Thank you very much for this talk. So my question is that you mentioned this global data assimilation, and probably you are addressing this like data assimilation in the atmospheric domain, right?
Yeah.
Okay. Did you have some evidence about how this actually works when you don't have like observation in certain regions, for example? So I don't know if it's the case of data assimilation in atmosphere, but if you have, if you have evaluations on part of the globes with very like rare observation, very limited observations.
So maybe I can show you this plot. So you can see that for the spatial correlation, there are some correlation between different grids, right? So even it has a long distance, maybe we can have the correlation to spread it. And also with the dynamic constraint, maybe when we correct the fields, maybe for example here, and with the dynamic constraint, you can improve the forecast here. So yeah, it can spread the observation effect to other regions without the observations. Yeah, it depends on the correlation and the dynamic constraint. Yeah.
So you are able to always correct the background towards I mean, even if you don't have observation in that region, so you are able to consistently provide better representation of that region.
I have to say the observation is very important, but if we have so when we don't have the observations, we can spread the effect from other regions to this region. Yeah.
Okay, nice.
Yeah, but it would better have the observations at that region if you really want to improve the forecast and analysis there. Yeah.
Okay, thank you very much.
Hi, Hung. Very impressive talk. I'm wondering, could you go back to the OBA method, I think?
Which one?
OBA.
Oh, okay.
When you're constructing, yeah.
So you want this one? Or the
Yeah, I guess maybe I guess I'm wondering when you're putting the pseudo observations into latent space,
okay.
what training, what is your training? Are you using ERA5 as your training or
It
do
depends.
that?
So this method is a self-supervised learning framework, right? And we can show you these slides. Sorry. It's a self-supervised learning model, so we don't need so the model cannot recognize the accuracy of the fields. They can only recognize the structure of the fields. So the structural realism is more important than the numerical accuracy. Yeah. So we also try to use here. So we also try to use the forecast results, forecast fields to train with large arrow to train this model. And we also find that the performance is almost is a little bit worse than the model trained on the analysis. Yeah. So you can just use the model fields to train your model. You can use a forecast, you can use a reanalysis. Yeah. It depends on which region you want to apply this method. Is that clear?
I'll think about it, I think. I'm sure it makes sense.
Yeah, okay. Yeah.
I guess I'm just struggling to understand, how do you compare Z naught to Z?
Compare Z to what?
Okay. Sorry, it's ZO. Okay. So is it this? It's the same latent space for that the observer.
Yeah, it's the same latent space. So we have to.
And it's just defined based on what optimizes, and so you don't have to.
Yeah, we have to define the autoencoder at first, and they define the latent space. Yeah.
Can I ask a question?
Oh yeah.
So thank you for the great talk. I learned a lot. You mentioned that the encoder is not nonlinear. So I wonder when you do the data assimilation in the latent space, I wonder if that will when you transform it back, will that mess up the covariance? And because it's potentially nonlinear, do you have to do some transformation, or you can just keep it? Just don't need to think about it.
Actually, we find that the decoder and encoder is locally linear. So yeah, we don't solve this problem.
Then following up to Kate's question, so for the latent space of the observation, latent space of the main encoder, you just need to make sure kind of they're on the same dimension, just let it does its work in that latent space. That's all you need. Is that how you do it?
Sorry, you mean that how we define the latent space here?
No, I mean for your OL, O2L. Yeah, so you just make sure it's the same dimension. That's it, or
yeah. Okay. I know the question. So when we have the encoder, the learner encoder, we define the latent space, right? So for each sample, we can have the latent. For each model space, we can have its latent representation. And also with the pseudo observation, we can use the observation operator to get the pseudo observations. So for each sample, we could have the pseudo observations and has its corresponding latent representations. So can directly learn this. Yeah.
Oh, thanks. So that's how you ensure. Oh, okay. I think. Thanks.
Welcome. Thank you.
And if there are any other questions on Zoom, feel free to unmute or to drop your question into the chat box. Okay, thank you so much, Hang.
Thank you.